In today's lecture, we are going to start discussing about line integrals and surface integrals. To start with, we will first deal with line integrals. It talks about integrals of functions, of course, which are defined on Rn and taking values also in Rn. And suppose on Rn I have given a curve, I want to integrate the function over the curve. What exactly does it mean? That's what I am going to explain now. So suppose I have a function f defined on a subset A of Rn to Rn, where most of the time I am assuming n is strictly bigger than 1, of course. Usually they are called vector fields. That is, given an element of capital A, it assigns a vector which is fx. So x goes to fx, which is a vector now. This is a vector. So I can denote it sometime by f1x, f2x, f3x, the case n equals to 3, of course, or I can also use the vector notation, that is f1x I plus f2x j plus f3x k, the standard vector notation of R3. Now these are called the vector fields in space because n equals to 3. Accordingly, we can define vector fields on plane also, that is the case n equals to 2. Now in whatever I am going to do, I will assume that capital F is a continuous function. Okay. Now suppose I have a curve. What do we mean by a curve? Well, it's a map C defined on some closed interval AB to Rn. I will usually work with n equals to 3, that is a space curve. If I choose n equals to 2, I will call it a plane curve. Now that means the curve is usually denoted by this also, Ct equals to xt, yt, zt. Okay. For example, I can look at this kind of a curve, that C of t equals to a cos t, a sin t, and then t. This is certainly a curve. So that is a continuous function. So I will demand a property on C, that is, we'll assume, that means I am looking at some specific kind of curves which has certain analytic property that would help me in defining line integral. The property is that C prime t is a continuous function of t. Okay. With this data, now I am going to define the line integral of a vector field f over a curve C. What do I mean by this? Well, the symbol for the line integral is integral over C f dot ds. I will explain what is the meaning of this symbol. The meaning is this following integral, integral a to b f of ct dot c prime t dt, where C from AB to R3 is a curve. Of course, it is a curve with the assumption which I have assumed that C prime is a continuous function. Now let us look at the definition again. Now Ct is a vector because C is a curve in R3. Throughout I am going to work with n equals to 3, so it is always R3, but there is no loss in generality in saying that. So Ct is a vector, it makes sense to apply f on that vector. As a result, f of Ct is a vector. Now if I look at C prime t, that is also a vector, because what is C prime t? In the parametric notation it is just x prime t, y prime t, z prime t. Okay. So given a value of t, this is a vector, f of Ct is also a vector, so it makes sense to talk about the dot product of these two vectors. As a result, then I get a scalar valued function. And what is the domain of definition of the function? That is f of Ct dot c prime t. Well, t varies on the closed interval ab, so it defines a function from closed interval ab to r. And all because of all the continuity assumptions which I am having, because my vector field is also a continuous function, C prime is continuous, that means obviously C is continuous. It turns out that the integrand actually is a continuous function of t, and hence it is integrable. So we do the ordinary Riemann integration of this function. This is called the line integral of the function over the curve C. To understand the definition more clearly, let me look at an example now. So I will give you a particular vector field now. So the example I have in mind is given by, so let me define the vector field as f of x, y, z, which is defined now as cosine of z, then e to the power x, then e to the power y. This is certainly a vector field. Now I define a curve, that is C of t. So the curve is defined as 1 t e to the power t. And what is the variation of the parameter? Well, let us say 0 lesser equals to t lesser equals to 2. And I want to calculate integral over C f dot ds. For that, what is the first thing I need to do? I need to calculate what is f of Ct. Well, the first thing I will calculate first is C prime t, which seems to be easier. C prime t is 0, 1, e to the power t. You can see what I am doing. I am just differentiating each component with respect to t. Then I have to calculate what is f of Ct. So f of Ct equals to f of 1 t e to the power t, which then by definition of my vector field is cosine of e to the power t, then e, then e to the power t. Well, that is f of Ct. Now I just look at this integral, integral 0 to t, 0 to 2 f of Ct dot c prime t dt equals to integral 0 to 2 cosine of e to the power t e to the power t dot now c prime t, which I know is 0, 1 e to the power t, then dt. I can calculate this vector product very easily. It is integral 0 to t, 0 to 2 e plus e to the power 2t dt. If I do this integration, what I get is et plus e to the power 2t divided by 2, and then I look at the limit 0 to 2, which you can very easily calculate. Just put the values of t, we get the line integral of the given vector field over the given curve. Now in some of the calculus books, you can see an alternative expression of the line integrals, that also I will explain now, that given the curve Ct, which is written as xt, yt, zt, I can write c prime t as dx dt, dy dt, then dz dt. Okay. Now this can be formally written as c prime t dt equals to dx okay, and if the vector field f is given as f1 I am suppressing the variables, of course, that you can see. It should actually be f1 of xyz I plus f2 of xyz j and so on plus f3 k. Then integral over c f dot ds, that turns out to be integral a to b f1 dx plus f2 dy, just taking the dot product, plus f3 dz. Okay, what it means is, it is integral a to b f1 dx dt plus f2 dx dy dt plus f3 dz dt and then dt. Okay, the formal expression of this kind you can see in calculus book written of line integrals. It actually means the previous definition, which can be alternatively expressed as the last equality which I have written in terms of the components of the function capital F, that is the vector field. Now for the, as far as the calculation of line integrals are concerned, you can see that it can be very difficult if the integral ultimately which you are getting as f of ct times c prime t, if that is complicated. But for certain functions, the line integrals actually become much easier. Now we will go to those cases. So let us start with some simpler kind of line integrals. Suppose I have a function f which is a function from R3 to R. So this is a scalar field, no longer a vector field. This is a scalar field because the value of the function is a real number. Now out of this scalar field, if f is differentiable, I can manufacture a vector field out of this f the following way. That is the gradient of the function which you are already accustomed with. That is, so gradient of the function is del f del x, del f del y, and then del f del z. Okay. Now assume that grad f is continuous. So I am putting two conditions on f, that first of all it is differentiable so that I can talk about the gradient. Second, the gradient is a continuous function. So it is a continuous vector field now. And suppose C is a nice curve, that C is a curve, that means C prime is continuous. I am always using this property on the curve. Then I can always think about integral over C grad f dot ds. Okay. Let us say C is from AB to R3. So what is this integral? I want to say it becomes something simpler. If C of A equals to x0, y0, z0 and C of B equals to x1, y1, z1, then it turns out that this is equals to f of x1, y1, z1 minus f of x0, y0, z0. Okay. So this you can actually see is a very neat analog of the second fundamental theorem of calculus, that integral of f prime is fp minus fa. It is more or less an analog of that, and that is not just an accident. This result can actually be proved using the second fundamental theorem of calculus. Okay. So let us see how to prove this. What I do is I define a function h from AB to R. It is given by the formula h of t equals to f of ct. Notice that C being a curve is a map from R to R3. F being a scalar field is a map from R3 to R. So as a result, F compose C is a map from R to R. Okay. H is essentially F compose C, it is only the domain of C imposed there, that is why it is a map from AB to R. Now H turns out to be a differentiable function because of the assumptions which we have. And now I want to calculate what is H prime at t. Now if I use the chain rule of several variable calculus, which you have learned already, what I get is that this is grad f at ct dot c prime t. This implies that integral over c grad f dot ds is nothing but integral from a to b, by definition grad f at ct dot c prime t equals to integral a to b h prime t dt. And now I can use fundamental theorem of calculus to get that this is hb minus ha. Apply this to the definition of h to get that this is f of cb minus f of ca, that is f of x1, y1, z1 minus f of x0, y0, z0. This is precisely what we wanted to prove. Now before observing some more things about this result, let us see how does it make our life easier. So I will try to calculate another line integral. In this case, to make things simple, what I will do is I will concentrate in the two-dimensional case. So let us take this force field, that f of xy equals to yx. So this is a vector field, and now I take a curve. So let us take this curve Ct equals to t to the power 9 sin 9 pi t by 2, okay, where 0 lesser equals to t lesser equals to 1. Now suppose I want to calculate this line integral. So first I need to know what is f of Ct. I will calculate that. This turns out to be easy. This is sin 9 pi by 2t, then t to the power 9. Then I need to calculate what is C prime t, that is 9 t to the power 8, then 9 sin 8 pi t by 2 times cosine pi t by 2 times pi by 2, okay. And then I need to look at the line integral, that is f dot ds, that is integral 0 to 1 f of Ct times C prime t. If I calculate this, what I get is 9 t to the power 8 sin 9 pi t by 2 plus 9 t to the power 9 sin 8 pi t by 2 cos pi t by 2 times pi by 2, this whole thing dt, which you can see is quite a complicated integral. It might be very difficult to solve this, calculate this integral explicitly. So instead of that, what I do is, what we have observed in the previous case, we will try to do that. That is, I will try to realize this capital F as gradient of some function, and that is very easy. I will just look at this function f of xy equals to xy. This implies then that grad f at xy, that is del f del x, which is y, comma del f del y, which is x, that is capital F at xy, okay. And then I notice what is C0. From the definition of the curve, it is clear that C0 is 0, 0, and what is C1? That is again very clear that this is 1, then sin pi by 2 to the power 9, that is again 1. So by the previous formula, it turns out that integral over C f dot ds is nothing but integral over C grad f dot ds. That means it is f of C1 minus f of C0, which then is f of 1, 1 minus f of 0, 0. But I know my definition of f, it just multiplies the x coordinate and y coordinate. That means f of 1, 1 is 1 and f of 0, 0 is 0. That means the line integral is actually equals to 1. See how complicated the previous integral was, but that does not really mean that the line integral is complicated to calculate. Once we have used the fact that this given vector field capital F can be thought of as gradient of a scalar valued function, it becomes easy using the analog of the second fundamental theorem of calculus. Now let's go back to the observation. What I have proved is that integral over C grad F dot ds is f of x1, y1, z1 minus f of x0, y0, z0. It means that if I am integrating a gradient over a curve, then the line integral does not really depend on the trajectory of the curve. It just depends on the initial point of the curve and the final point of the curve. Whatever way the curve joins those 2 points, the integrals are same if the integrand is a gradient. That is what follows from here, that if I have a point here and I have a point here, I can join it this way. I can also join it this way, you know. So this is C1, this is C2, and my capital F is some grad F. Then from the previous formula it follows that integral over C1 grad F dot ds equals to integral over C2 grad F dot ds, because the result depends on just the final point and the end point, final point and the initial point. Okay. But in general that is not the case. If you have given a line integral of an arbitrary function which is not really a gradient, then the integral can depend on the trajectory of the curve. That is, it might matter how those 2 points are joined by a curve. So I will give an exercise here, you can check it yourself. Consider the vector field f of x, y, z equals to yi minus xj plus k. Okay. And let us take these curves. First one is C1t. I define it as cosine t, sine t, t by 2 pi. Then I define C2t as cosine t cube, sine t cube, then t cube by 2 pi. Here 0 lesser equals to t lesser equals to 2 pi. Here 0 lesser equals to t lesser equals to cube root of 2 pi. And then I define C3, another curve, that is cosine t minus sine t, t by 2 pi, where 0 lesser equals to t lesser equals to 2 pi. Now just check the following, that integral over C1 f dot ds, that turns out to be equals to minus 2 pi plus 1, integral over C2 f dot ds, that is minus 2 pi plus 1, and integral over C3 f dot ds, that turns out to be 2 pi plus 1. Okay, just calculate these integrals, it is essentially easy. You will observe this. Notice that the first integral and the second integral, they have different values, but the final point is 2 pi, the initial point is 0, they are joined by 2 different curves actually, and then it turns out that the integrals are different. That means in general it can happen that the line integral of a function over 2 different curves but joining the same points can be different. But here something has also happened, that integral of the function over C1 and integral of the function over C2 has become equal. Well, this is not just a happy accident, this happens because of the following fact. Let me explain to it. So suppose I have a curve C which is from AB to R3, and suppose I have a map H which is from UV to AB. Assume that H and C has the property that C prime and H prime both are continuous. Okay. Now I can form a new curve, call it B. So B is a curve which is defined on UV, goes to R3. It is defined as B of S equals to C of HS. Okay. Then B defines a new curve. I want to know what is integral over B f dot ds. Okay. F is a given vector field. I want to integrate f over B. Well, usually this new curve B which I have defined, it is actually not new. It is the same curve because the image is same as the image of C, but the space of parameters now are coming from UV. So this is usually called a reparametrization of the curve. Okay. Now I want to calculate what is integral over B f dot ds. So what I do is I just write down the definition. So this is integral from U to V f of bs dot b prime s ds. Okay. Now I write it down. It is integral U to V f of C of Hs times I have to calculate what is B prime, that is H prime S times C prime at Hs by chain rule times ds. Okay. Now I do a change of variable to put Hs equals to t, and then let us see what do the integral change. Well, if Hs equals to t, then the limits of integration will certainly change from Hu to Hv. Okay. And then f of C of t, because earlier I had f of C of Hs times, now comes, look at the integral again, it comes to H prime S then C prime Hs, but Hs equals to t, I am using the change of variable, it just changes to C prime t dt as H prime S ds is equals to dt. But now observe that Hu is equals to A and Hv is equals to B. So what I get is f of Ct dot C prime t dt, which is nothing but the line integral of f over the curve C. Now if you look at the previous example, what was my C1? C1 was cos t sin t t by 2 pi, where 0 lesser equals to t lesser equals to 2 pi, and C2t was cos t cube sin t cube then t cube by 2 pi, where 0 lesser equals to t lesser equals to cube root of 2 pi. So in this case what actually has happened is I have defined a map H from 0 then cube root of 2 pi to 0 to 2 pi given by Ht equals to t cube. Okay. And then my new curve, if I look at the relation, C2 is actually C1 of Ht. So I will repeat again what we have observed here. Suppose f is a vector field given, C is a given curve, B is another curve which is a reparametrization of C. I have just defined what does it mean to say that B is a parametrization of C. That means the parameter spaces are given by some differentiable function, they are connected by some differentiable function H, that is B equals to C compose H. Then integral over C f dot ds, that is integral over B f dot ds, that is the line integral does not change even if you change the parametrization of the curve. Okay. Now we will go to a different meaning of line integrals, but before that there are some elementary facts about line integrals which can be easily proved. One is, suppose you have given two curves C1 and C2, then you can talk about C1 plus C2. What does it mean to say C1 plus C2? So I will just explain it by picture. Suppose this is C1, it starts from A, goes to B, then from B it goes by another curve, let us say, which is up to C. So the domain of C1 is AB and domain of C2 is from BC. Then from C1 and C2 I can talk about the curve C1 plus C2, which is defined as this is equals to C1t if A lesser equals to T lesser equals to B, and equals to C2t if B is lesser equals to T lesser equal to little c. Only care has to be taken that C1b equal to C2b, only then you can join the curve. Okay. In that case one can show that integral over C1 plus C2 f dot ds, that is equals to integral over C1 f dot ds plus integral over C2 f dot ds. It follows just from the definition of the line integral. Similarly, one can take the negative of a curve also just by changing the direction. Suppose this is my curve C. Okay, this is the initial point, this is the final point. Then I can look at the same curve but now in a reverse direction. It goes this way, let us say. I can come back this way. So if this curve is C, this is called minus C. And then using the definition of line integrals again one can check that integral over C f dot ds, that is minus integral of f dot ds, which is integrating the function over the curve minus C. These two facts I will be using later. They can be proved just by the defining properties of the line integrals. It's nothing serious. Now let's shift to another geometric way of understanding the line integrals. So what we observe first is the following thing. Let us say C from AB to R3 is a curve with the property of course that C prime t is continuous. Now I also assume that C prime t is non-zero for all t. So it's an additional property I am throwing in. In most of the cases you will have this property satisfied, that the derivative of C is always non-zero. Then I can form the unit tangent vector. I will call it Tt, capital T of t. This we know is defined by C prime t divided by norm of C prime t, so that it has unit length. Now the element of arc length ds, that is I know is norm C prime t dt, because I know that this is square root of x prime t square plus y prime t square plus z prime t square. This is a result which we have proved while talking about length of curves. We have done the thing only on R2, but the analogous analysis can be done on R3, and you can show that the length of the curve is actually given by norm c prime t dt. So all I am saying is that this formula we have seen and actually proved in 2 dimension. I am saying stating the same formula in 3 dimension. So I will write again what we have proved, that this is norm c prime t dt, which is the element of arc length ds. So this implies then that c prime t dt, if I look at that, okay, that is c prime t by norm c prime t ds. Correct? How did I get this? Because ds is norm c prime t dt, so just formally look at it this way, that dt equals to ds by norm c prime t. So c prime t dt is c prime t by norm c prime t ds. Okay, this is just a formal way of saying this, but this then, by my definition of the unit tangent vector, is tt ds. Okay, now this has some implication. The implication is integral over c f dot ds now can be written as integral a to b f of ct dot c prime t dt, which is our usual definition, is same as integral a to b. I am not changing f of ct, that stays, dot, now c prime t dt I can write as tt ds. Okay. So, but what is f dot t? What does this mean? It means actually the projection of the vector field f in the direction of the tangent vector to the curve. Okay. So this implies then, so I will write it, the meaning as the line integral now of f on c is the integral of the tangential component of f with respect to the arc length. So I will repeat again. What I have shown is that integral of f over the curve c is integral a to b f of ct dot tt ds. Okay. Now f dot t is the tangential component of the function in the direction of the tangent t on the curve c. So what I am doing is I am looking at the tangential component of the function. This tangent is of course drawn on the curve c. That component is now getting integrated with the arc length of the curve. That is another meaning, a geometrically related fact about the line, because you can view the line integrals in this way also. It is interesting to observe that line integrals can actually be connected with the work done by a force field also. That is what we are going to do now. So suppose F is a constant force field, it acts on a particle and produces a displacement d. D on a particle. Then we can actually calculate what is the work done. Work done in this case is F dot D. Now if F is not constant, then we want to know how does one calculate the work done by this force field. This is where we are going to bring in the theory of line integrals. For that, first I need an analog of the Riemann sums, which we have done in the one variable case. In this case, the situation is as follows. So I take a partition of the parameter space A, B by T0, T1 to Tn, let us say. Let us take some sample points ui in the interval Ti minus 1 Ti. And I look at the sample values, that is f of Cu, where f is a given force field. And then I can look at this Riemann sum, summation I from 1 to k f of C of ui times then the vector dot product C Ti minus C Ti minus 1, okay, which is equals to summation I from 1 to k f C ui dot product delta Si. Now it can be shown that if I take finer and finer partitions, that is the norm of this partition going to 0, that means the maximum length of this partition, which is the norm of a partition, if that goes to 0, one can show that this delta Si actually better and better approximated by C prime T dt, and this sum actually converges to the line integral, that is A to B f of Ct dot C prime T dt. Okay, it can be shown, but the proof of that is beyond the scope of this lecture, so we are not going to prove it. Let's just assume this, that this line integral can also be viewed as Riemann sums, the limits of the Riemann sums. Now using this, let us go back to the question of work done again. Suppose F is not a constant vector field in general, not a constant force field, it acts on a particle and produces a displacement, let us say delta S1. Then the work done is approximately equal to F dot delta S1. If in the subsequent time it produces a displacement of delta S2, then the work done is approximately equal to F dot delta S2. So the total work done is F dot delta S1 plus F dot delta S2, and so on. Now this subsequent times which we are using is actually a partition of the parameter space, and then using the Riemann sum one can actually prove that the total work done by a force field F, here we are displacing along a curve C, let us say, along a curve C, otherwise delta S1 won't make sense, along a given curve C. In that case, the total work done using the theorem of Riemann sum turns out to be integral over C F dot ds. Okay. Now I have not given the proof of all this, but let us illustrate it by an example. So first I will give you a force field, then a curve. Well, the force field which I give is f of xyz equals to x cube I plus yj plus zk. Okay, and the curve which I give is the circle of radius a in the yz plane. So then I can write down the equation of the curve also. So this is Ct, since it is in the yz plane, its first component is always 0, then a cosine theta, a sine theta. Okay, 0 lesser equals to theta, lesser equals to 2 pi. So the question I am asking is, suppose I have a particle at the point 0, let us say, and then I apply this force field. This particle moves around the whole circle, comes back to 2 pi. If that happens, I will try to calculate what is the total work done. Well, what happens in this case? Well, it is c theta. First I have to calculate c prime theta, that is 0 minus a sine theta, then a cosine theta, and then I have to calculate what is f of Ct. So in this case it is f of c theta, that is, I obviously get 0 here, then a cosine theta, then a sine theta. Okay, then what is f of c theta dot c prime theta? That is 0 a cosine theta, a sine theta dot 0 minus a sine theta, a cosine theta. If I do the dot product, what I get is minus a square sine theta cos theta plus a square sine theta cos theta, that is equals to 0. What does it mean? It means the force field is actually in the normal direction of the circle. So if this is the circle in the yz plane, this is my x-axis, then the force field is actually acting in the normal direction. That means it cannot move a particle along this curve. That means the total work done by this force should be 0. That means integral of f over c dot ds should be equals to 0. But this, by my definition, is 0 to 2 pi f of c theta dot c prime theta d theta. But I have already calculated that f of c theta dot c prime theta is actually equals to 0. So this is equals to 0. So it matches with the physical observation. So now let us sum up what we have learnt about line integrals. First, we have defined line integration of a vector field over a curve C, of course under certain conditions on the vector field and the conditions on the curve. The condition on the vector field is that it should be continuous. The condition on the curve is that C should be a differentiable function. Next, we have shown that there exists an analog of the second fundamental theorem of calculus when the vector field in the question is gradient of a scalar valued function. In that case, many line integrals can be easily computed, and we have given one such example. Then we have noted some elementary properties about line integrals, one of them being that if I reparametrize the curve, then the line integral does not change. Then we had a geometric viewpoint towards the line integral, where we have proved that if a vector field f is given, then its line integral over a curve C is nothing but the integral of the tangential component of the function with respect to the arc length. And then comes the last topic. We have shown that line integral actually represents, physically speaking, the work done by the force field F in displacing a particle over a given curve C. In the next lecture, we will start with surfaces and integrals of functions over given surfaces.